Hello everyone, this video tutorial introduces the application of automated workflow for predicting skin sensitization. The QSAR Toolbox has been enriched with data and features over the years, making the system one of the richest, containing a huge thesaurus of knowledge and data that can be used to fill data gaps and for other purposes. Automated workflows for the prediction of toxicological endpoints have been developed to facilitate users' work and analyses. The workflows are applied automatically and are designed to generate reliable predictions based on a predefined algorithm. The algorithms include the application of specific profilers, data sources, and data gap filling techniques depending on the endpoint for which they have been developed. Currently, the Toolbox installation provides automated workflows for predicting acute aquatic toxicity to fish and skin sensitization. The aim of this video is to demonstrate the automated workflow for predicting skin sensitization. If you are interested in the prediction of acute aquatic toxicity to fish, please watch the corresponding video tutorial. The skin sensitization prediction algorithm consists of several steps and is explained in more detail in a few slides. The purpose of developing the automated workflows is to predict different endpoints of skin sensitization, such as EC3 associated with the local lymph node assay, the guinea pig maximization test, the combination of LLNA and GPMT, and the skin sensitization for defined approaches. The automated workflow for skin sensitization automatically applies functionalities from the profiling, data, category definition, and data gap filling modules. The automated application is based on a predefined and implemented algorithm, which is briefly explained on the next slides. Here is a schematic representation of the algorithm for predicting skin sensitization. Once a chemical is entered into the system and the workflow is started, the substance is automatically profiled by the corresponding profilers with protein binding alerts and a list of structure-based profilers. The abiotic and biotic transformation products are also simulated and checked for activation according to the respective profilers with protein binding alerts. The corresponding databases with skin sensitization data are automatically selected. In addition, the primary group is defined based on the profiling result of the target chemical. If a protein binding alert is identified in the structure of the target chemical, the primary group is defined based on the identified protein binding alert. If the target chemical is activated by abiotic or biotic transformations, the primary group is defined taking into account the metabolic activation of the target substance. In addition, a mandatory list of predefined profilers is applied as subcategorization, and if any analogs remain after the final subcategorization, the target chemical is predicted based on the final list of analogs. If there is no alert in either the parent chemical or its abiotic and biotic products, the primary group is defined based on structure-based profilers. A predefined list of structure-based profilers is used, and the group with the most analogs is selected as the primary group to fill data gaps. A list of mandatory subcategorizations is then applied, including protein binding profiles that take into account the metabolic activation of the analogs. The reason for this is to remove any analogs that are collected by a structure-based profiler but are further activated. The prediction is based on the closest analog that remains after the last subcategorization. If no analogs are found or remain after the last subcategorization, the target chemical is not predicted. Now let us go to the QSAR Toolbox and run example chemicals. The automated workflows can be run for a single chemical or a list of chemicals. In general, there is no limit to the number of chemicals in the list. However, if it is a large list with hundreds of chemicals, there may be issues with memory usage. From the input, go to Chemical List section and click on the arrow of the List button. Select from the Examples folder in the menu. Search for this example and select it. Confirm the displayed message with No. 19 substances are loaded into the data matrix. To run an automated workflow, you need to go to the Data Gap Filling section and select the Automated button. This will display the list of available automated workflows for predicting different endpoints. Select the workflow from the list. This is the workflow that combines skin sensitization data from mice and guinea pigs. Use the question mark to see more details about the algorithm of the corresponding workflow. To run, view or cancel the workflow, use the corresponding buttons at the bottom. Let us execute the workflow. Now we can change the defined range, which currently includes applying the workflow to the entire group of 19 chemicals. Let us change it to start from 5 to 10, which defines the range of chemicals for which the workflow will be executed, from chemical number 5 to chemical number 10. Using the checkbox below, we can enable the generation of the document tree levels, which show exactly what happens for each of the predicted chemicals. Note, however, that it is better to keep the default setting and not save the prediction workflow when running the workflow for a larger list of chemicals, as this will cause memory consumption issues. Click the OK button and wait for the workflow to complete. At this point, we can see how it works on the screen. Finally, a message will appear stating that the predictions are complete. Now we can see the predicted result for the 6 selected chemicals in the data matrix. We can also see the individual steps that were performed to obtain each of the predictions by selecting the levels of the document tree. Congratulations! You are now familiar with the automated workflow for predicting skin sensitization. To learn more about the automated workflow for predicting aquatic toxicity to fish, please watch the corresponding video tutorial. If your question concerns policy or regulatory acceptance of Toolbox results within EU regulations of ECHA's competence, please refer to the ECHA website directly.